Alright, hey guys, we are going to talk about trig equations. This is the second half of chapter 5. It does get a little easier than trig identities. It's going to put together algebra, solving linear equations, factoring, solving quadratic equations with inverse trig. So you might want to have handy the little trig chart that I drew up here in the corner. If you have your copy, and there is a blank copy of this note sheet on the agenda for today, or you can just write down the examples in your notebook if you'd rather do that. So basically what we're doing here is we're going to start with this example, sine x equals a half, and we're going to think about it in terms of the graph. So I have drawn for you here just the basic trig graph. 0 up to 1, back to 0, down to -1, back to 0. That's graphed for just one period. And then I'm going to add to that graph the line y equals a half. Alright, so basically the solutions here would be what are the intersection points between the sine graph and the graph of 1/2. So just in one period, I have two intersection points here and here. So those are my solutions. Now I can't really figure that out from the graph necessarily, so I'm going to try in this little box to the side here to solve it algebraically. So sine x equals a half. We want to solve this for x. You cannot divide by sine because division is not the reciprocal of sine. Instead, we want to solve for x by doing inverse sine of a half. Now we're going to throw out all the domain restrictions and everything we memorized for inverse trig. Now we're back to just remembering the ASTC trig chart and knowing which trig functions are positive in which quadrant. So sine is positive in two quadrants. It's positive in the first and the second, so that's going to be my two solutions. And I know, again, I have two solutions because of the intersection points on the graph, that visual. So now I'm going to use inverse trig. Go to your chart, look at sine, what angle is sine equal to a half, and that would be at pi/6. The first quadrant answer, and then the second quadrant angle for pi/6 is 5pi/6. So that's my second answer. So those are my two x values, pi/6 and 5pi/6. Now those are what are called specific solutions, and that's referring to solutions within a specific domain. The domain we're always going to be using is from 0 to 2 pi. And the reason why we have two different types of solutions is because trig functions or trig graphs are periodic. And so technically, and you can see this on the graph, that's why I graphed more than one period, technically we have an infinite number of solutions because that graph just keeps going and going. So you can see I have two more. If that graph were to extend into the negatives, I would have two more. So that's called general solutions. Those are all possible solutions. And obviously, if you're giving general solutions, you don't want to have to write infinite numbers. So we are going to do that by writing multiples of pi/6. So I write pi/6 plus 2 pi k, meaning I go around a circle, the unit circle again, 2 pi, and I get another answer. I go around again, add 4 pi, get another answer. Go around again, add 6 pi, get another answer, so on and so forth. So you do the same thing with the second quadrant answer, 5pi/6 plus 2 pi k. So if you're asked for general solutions, that's how you write it, but throughout this whole section and tomorrow's section, we will be giving specific solutions. So you don't have to worry about the 2 pi k. You would just write, in this example, pi/6 and 5pi/6. All right, so that's a general overview. Obviously, you don't need to draw a graph for every single one of these problems. So I have two examples below here that starts you out pretty easy that we're going to do just algebraically using the trig chart. So the first thing you do is solve for theta by doing inverse trig, so inverse sine square root 3 over 2, and then you ask yourself, sine is positive in what two quadrants? So again, that is first and second. So I'm going to get two solutions. The first solution you can get out of your trig chart, just look for sine being equal to square root 3 over 2, and that happens at pi over 3. And then the second quadrant angle for pi over 3 is 2 pi over 3. So that's your second solution. Alright, let's switch over to cosine. Cosine equal to a negative. So I'm going to throw two different things in there. So first thing you do is solve for theta. And so we're going to do inverse cosine negative root 2 over 2. And so I'm thinking, first of all, in what two quadrants is cosine negative? So that happens in the second and the third. So my two solutions need to come from those quadrants. You look at your chart, trig chart that is, to get the reference angle, and that would be, of course, pi over 4. And then give me the second quadrant angle for pi over 4, which is 3 pi over 4. And the third quadrant angle, which is 5 pi over 4. And that's my two solutions. Alright, so on the next page, we're going to get a little bit harder, and we're going to look at using some algebra techniques along with your inverse trig. And so we're going to look at some linear examples, like you would solve a linear equation, and then several different types of quadratic examples. And we're still going to be using that trig chart, so you still may want to have yours out. Alright, so I pulled some linear examples. And so to start these out, you need to solve for the trig function. Make sure that's the only thing on the side. So cosine theta then is equal to negative 1. And then you solve for theta using inverse trig. So where does theta equal the inverse cosine of negative 1? Now that's on the quadrantals. So I'm thinking, what angle does cosine equal negative 1? And so I'm thinking, you know, I've got 4 points. Which one has an x value of negative 1? So that's over here. Negative 1, 0, and that's at pi. So this answer would be only pi. You don't have to get two solutions if you're on the quadrantals. So that would be the only answer. Okay, let's move on to something a little bit harder. Here again, we need to solve for sine theta. Generally can do that in one step, so I would subtract 1, divide by the square root of 2. Now, just looking at that, you might think, well, that's not in my trig chart. I don't know what that value is. Well, you need to rationalize first. So over here to the side, I'm going to multiply that by square root 2 over square root 2. That's going to be negative square root of 2 over 2. And then you start to realize, oh, I do know that. So where does sine theta equal negative root 2 over 2? So that's saying the angle whose sine is negative root 2 over 2. Now sine, and I'm just going to rewrite my ASTC over here. Sine is negative in the third and the fourth quadrant. So that's where the two answers need to come from. The reference angle is pi over 4. So the third quadrant angle for pi over 4 is 5 pi over 4. And the fourth quadrant angle for pi over 4 is 7 pi over 4. So that's my two solutions. Alright, now we've made it to the Mac Daddy quadratic problems. These are obviously the trickiest, but if you understand basic factoring, we're just going to apply it to trig. So the first method here is square root method, and just like in algebra, you're going to know you're going to use the square root method if what you're dealing with is a binomial and you only have one trig function in your problem. The other thing you have to make a huge note of is that when you take the square root of something, you need plus or minus in front of your answer. In this case, if you do not put the plus or minus, then you're going to miss out on some of your answers. So star that, make a note of that, something. Alright, so to do the square root method, we always start out by solving for the trig function first. So I'm going to say tangent squared is equal to 1 over 3, and then you're going to square root both sides. Now, square rooting a fraction sometimes throws people. Basically, you square root the numerator and the denominator separately, and so that actually gives you 1 over the square root of 3, which you then rationalize, and that gives you root 3 over 3, and you start to recognize it. Now, again, tangent theta is equal to, here's the important part, plus or minus root 3 over 3. The reason that's so important is because I have to include all the quadrants where tangent is positive and all the quadrants where tangent is negative. Well, that's all 4 quadrants. So anytime you're doing the square root method, your answer needs to be all 4 quadrants. So you get 4 answers, not 2. So thinking back to my trig chart, I'm going to go back a screen for a second. Tangent root 3 over 3 is all your pi over 6 angles. So that's going to be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. As we said before, 4 answers. Okay, rolling right along. We're going to do a reciprocal function, because those are always fun. Throw in a reciprocal. So we're going to solve this one for secant squared. Add the 2. Take the square root of both sides. And again, do not forget that that's plus or minus the square root of 2. Now, our brains typically don't think well with reciprocal functions, so I'm going to actually do the reciprocal of both sides. The reciprocal of secant is cosine, and the reciprocal of the square root of 2 is 1 over the square root of 2, and I'm going to write that to the side so I can rationalize it. So that's going to be plus or minus root 2 over 2. So then I'm doing the angle whose cosine is square root 2 over 2. That, of course, is pi over 4. And because of the plus or minus, that's going to be all 4 quadrants. So 3 pi over 4, 5 pi over 4, 7 pi over 4. So as I said, once again, that's the one people always mess up. If you are doing it with the square root method, you need 4 answers, not the typical 2. Alright, best for last, factoring methods. There's 2 different types of factoring that may show up. You have trinomial factoring, where you look for factors of C that add to give you B, or you can have GCF factoring. So I've pulled an example of each. The factoring with the trinomials sometimes really confuses people, so my suggestion is to do a variable substitution and just make that x squared minus x minus 2 and factor it like you normally would. So x and x multiplies to give you negative 2, adds to give you negative 1 would be negative 2 and positive 1. And then go back and put sine instead of x. So that's sine theta minus 2 times sine theta plus 1. You're going to set both of those factors equal to 0 and solve for theta. So that gives you sine theta equals 2. Sine theta equals negative 1. Do inverse sine and inverse sine. Now, inverse sine of 2. Thinking back to inverse trig. If I try to do a reference triangle, I'm going to use this space up here because that's not on the unit circle, so maybe you have to use a triangle. Well, then you're going to do opposite is 2, hypotenuse is 1. That doesn't make any sense, so that's no solution. Any value for inverse sine greater than 1 is going to give you no solution. So that side, nothing. Over here, we're thinking about the angle whose sine is -1. And once again, that's going to be on the quadrantals. So again, if you'll follow me up here to our diagram, a y value of -1 is down here at 3 pi over 2. So when you have a quadrantal, then you may only get one solution versus the 2 solutions, since we got no solution for the other path. All right, final example. Hope everybody's still with me. We are going to do GCF factoring for it. You see both terms have a cosine, so I'm going to factor out a cosine, which leaves me with sine theta minus 2. And then once again, you're going to set both factors equal to 0. So cosine theta equals 0. Sine theta is equal to 2. Once again, inverse sine of 2 gives you no solution, so that side, no answer. Sometimes you'll get answers for both, so don't feel like, it's always no solution. It's just these particular examples I pulled. Sometimes you'll get 4 answers because you'll get 2 from one factor and 2 from the other. Sometimes you'll get 3, sometimes you'll get 1, it just depends. So cosine theta equals 0, that's on the quadrantals once again. X values of 0, that happens at pi over 2 and 3 pi over 2. So for this example, you see we actually get 2 solutions. Alright, so I hope that's helped. This, once again, is the basic types of trig equations. Stay tuned tomorrow for the harder trig equations. Alright, see y'all later.